So how can I find the area between two curves? And I want to be clear, just let's look at this visually. Let's see what we're talking about here. If I have a curve here, and I have another curve here, and I have my two values, I'm going to make A here and B here. And I want to find the area between the two curves. So I'm looking for this section here. How am I going to do that? Well, I'm going to go just old school on this. I'm going to go back to your high school geometry class. You probably did a very similar question there. If I have a circle and I have another circle inside of it, how do I find the area here? The area between the two, right? Inside the outer circle and outside the inner circle. Hopefully you remember the way we did this is we found the area of the large circle, which was too much, right? Because that also includes this bit here. And then the way we fixed this is we just subtracted out the area of the smaller circle. Well, I'm going to do the exact same thing here. The exact same thing, I'm just going to do it with definite integrals. All right, so let me label these things. If I call the upper function f of x and the lower function g of x, then the integral from a to b of f of x is everything between f of x and the x-axis, including this part here that I don't want. All right, but how can I get rid of that? Well, I know what that area is. That's the area between g of x and the x-axis. So that green area is the integral from a to b of g of x dx. And if I subtract that out, I get the area between the two curves. Now, I'm not actually going to do it this way, because doing this way means I have to do once I have to find two antiderivatives, one for f and one for g, and then I have to do 4 evaluations. I have to evaluate a and b in this antiderivative, and a and b in this one. Okay, I can simplify this. I can make this easier. I'm going to use one of my integral rules that says the integral of a difference is the difference of the integrals. In other words, this integral is the same as the integral from a to b of f of x minus g of x dx. And there you go. For the cost of subtracting the two functions, which generally is going to be pretty easy to do, now I only have to find one antiderivative, and I only have to evaluate it at 2 values. So I have to do 2 evaluations. Okay, so let's see how this works. Right, I've got my 2 functions. I've got y equals e to the x and y equals e to the 2x. And now I want to do this between 0 and 3. So let's see. I'm going to sketch a quick graph over here because we kind of need to know who's on top, right? Which is the f and which is the g from my previous example. Well, let's see. I'm gonna go y equals e to the x first. And I know what it looks like. I'm just going to do some points. If I put 0 in there, e to the 0 is 1. And if I put 3 in there, e to the third is 20. So that's, it's an exponential function that grows super fast, right? It's up here someplace. This is 3, 20.1. And there is my y equals e to the x function. Okay, how about the other one? How about y equals e to the 2x? Okay, well that's going to start at 0 also. It's going to start at 1. If I put 0 in, it's e to the 0, that's 1. And if I put 3 in, well look, if I put 3 in, I get e to the 6th, which I know is greater than e to the 3rd. So this is going to be the upper function, and this is the area I'm trying to find. So the area between the two curves, will be the integral from 0 to 3 of the top function, that's e to the 2x, minus the bottom function, that's e to the x dx. Okay, now let's see. I can't combine those two. I can't simplify this any further. So I'm going to go straight to finding the antiderivatives. An antiderivative of e to the 2x, if you remember back to when we talked about integration by substitution, that's the method you would use here. If you do that, this is 1/2 e to the 2x minus e to the x. And I'm going to evaluate this from 0 to 3. All right, so putting 3 in, I get 1/2 e to the 6th minus e to the 3rd minus, I'm going to put 0 in, 1/2 e to the 0 minus e to the 0. And so let's see, I'm just simplifying. 1/2 e to the 6th minus e to the 3rd minus this, e to the 0 is 1, so this is 1/2 minus 1, which is minus 1/2, but I have this minus out in front here, so this turns into plus 1/2. 1/2 e to the 6th minus e to the 3rd plus 1/2. That's my area. Right, that's it. We're done. It's a perfectly good answer. Right? Don't do anything else with it. Okay, so let me ask here, what would have happened if I had screwed this up and gotten it backwards? Right? What if I had done the integral from 0 to 3 of e to the x minus e to the 2x dx? Right? Just by mistake. Right? Well, look, let's do this. Let's factor a minus 1 out of this thing. This becomes minus the integral from 0 to 3 of e to the 2x minus e to the x dx. This is the one I just did, right? So all that would have happened would have been my sign would have been wrong. It would have come out negative instead of positive. So just kind of be on the lookout for that, right? If you're looking for an area and you know that one function is always higher than the other, if the two functions cross, that's a case we're going to have to think about a little bit. We're actually going to talk about that in the next lecture. But if you're confident that one of your functions is always higher than the other, then you know the area is going to be positive. If it comes out negative, you kind of just got to second guess yourself, say, okay, well, did I get them backwards? And if you did, fixing it is just a matter of taking the absolute value. You don't have to do the whole thing over again. Okay, so let's take a look at another one. This one is a little different. I haven't been given the limits, right? I haven't been given the a and b. Okay, but we can find them. All right, here's what I'm going to do. Let's sketch a graph of this real quick. Let's see. I'm just putting some points in here because I want this to be fairly accurate. When x is plus or minus 1, we get 1. When x is plus or minus 2, we get 4. So it's going to look something like this. Okay, so there's the parabola. And the second function, y equals 4, that's a horizontal line. So that's this here. And I want the area between these two. So that's the area in this section here. Okay, so how am I going to do that? Well, I'm going to do what we did before. I know my y equals 4 function is on the top, and I know my y equals x squared function is on the bottom. In that area, right, that's the order. So my area is going to be the integral of 4 minus x squared dx. So what are my limits? Well, it's going to be this x value here and this x value here. So how do we find these limits when we aren't given them? Well, you set the functions equal to each other. X squared equals 4. Right? That'll give me the x values where the two y values are the same. And I can solve this. This is x squared minus 4 equals 0. Excuse me, now do it the easy way. Just take the square root of both sides. X equals plus or minus the square root of 4, which is plus or minus 2. So those are going to be my limits. And now it's just like all the other questions. Right? Let's find an antiderivative. 4x minus x cubed over 3 from negative 2 to 2. Let's put our numbers in. 4 times 2 minus 2 to the third over 3 minus, let's now do negative 2, right? 4 times negative 2 minus negative 2 to the third over 3. So this is 8 minus 8 thirds minus 8 plus 8 thirds. So let's see, 8 minus 8 thirds plus 8 minus 8 thirds. That's 16 minus 16 thirds. Let's do a common denominator here. 16 is 48 thirds. And now I can subtract these. 48 minus 16 is 32. 32 thirds is my answer. That's the area between those two curves. Okay, so what's next? We've got a few more to look at, right? That's a good start. But we do have a few more situations we need to take a look at so you're familiar with them.